Yeah, thank you for the opportunity for organizing this and for your interest in this as well. Because indeed, for me, it was just like the next event after this silence event, because it was the last one I went to before we stopped traveling. Anyway, welcome to this presentation about asymmetric quorums, asymmetric trust. And I want to explore a bit of the foundations of what it means for the protocol here to trust, not for human level, on our human level. This is joint work based on the joint work with some of my excellent students, Orestes and Luca, and also with Giuliano Losa, who is from Stellar, who is also here. Typically, we are using threshold trust, and you just heard it, majority. Yeah, majority sounds like, yeah, we have a majority of good guys. In those protocols here, we actually have a 2/3 majority, a strict 2/3 majority most of the time, but we are only trusting by the numbers. Yeah, we are trusting that a 2/3 or more than 2/3 of the nodes are doing the correct thing, and so this is the typical security assumption that we are working on. It doesn't really work. It's better. Okay, well, I can't say. I can't hear it, but you hear it. Okay, good. Thank you. Of course, it's not always the 2/3. It's sometimes the majority, sometimes less. But what if we think about this? Is it necessary to have this uniform view of one person, one vote? Yeah, one person, one vote, we believe. Yeah, may not always be the case in security assumptions. Yeah. It's only trust by numbers. We are only trusting by numbers in those protocols, most of them. And it's also, when you look at the stake-based protocols, there is the fungibility of money behind there, of course, but it's the majority wins. Yeah, the majority is right. There's nothing else than to say. If all the nodes are have the same voting power, it's an egalitarian model. Yeah, and this is also can be called democratic as well. Yeah? This is the first point I'm trying to make here. Yeah? We are respecting everybody's vote in the same sense, in the same way. There's also another aspect of this, namely, it's imposing on our security assumptions in the sense of that we are conformistic to this model. Yeah? We all have to adopt this security assumption. We cannot pick our own assumption if we don't like it. Yeah? If we happen to not like this. Yeah? We cannot express our individual preferences for this. And these two conditions, I'm going to relax them in the rest of the presentation and show you some work how this can be generalized. Yeah, the first step here is generalized trust, not defining our majority. I can't say majority because I don't want to say majority, right? Defining who is right, not by a majority. Yeah, this is actually work that goes back 25 years. Yeah. And Dari Malka is also here, has had defining or fundamental influence on this. What if we said, so this classic work has defined properties for so-called quorums, Byzantine quorum systems that don't start with quorums, but they start with an assumption about who may be faulty, which coalitions may fail. And if you remember the previous picture there were any subset of two that could fail. Any subset of two could conspire against the protocol. That's the assumption. Here, in this example here, we could say, oh, there is a coalition here on the upper half, X, Y, Z, and there's another coalition that could be in the lower half. It's P, Q, and R, and any two of them could conspire and work against the protocol, but only two of them in the same partition here, not two across. Any individual, yes, that's also transitively part of the what can be faulty. Now, a quorum system we can define from such an assumption then on the sets of nodes that may fail, and there are precise conditions on. No, this is shown later, but the faulty set, the potentially faulty set here is shown here. Any two from above, any two from below. And the corresponding quorum system is shown here below, which is usually in the canonical way just the complement within the set of participants that has to be known. This will come later again, within the set of participants of all these faulty sets. So that means all of them from below and one from above, or the other way around. Each of such group makes a quorum. And notice here that we have, we're going to have a Byzantine quorum system from which this assumption we can run consensus protocols, and we have only 6 nodes. We don't have 7, right? In order to tolerate any 2, we would need 7. Yeah. Here with 6, we can have, because we have a stricter assumption, we can have a different protocol that does not result as a generalization of the previous one. So here, not all the nodes are equally trusted, but notice the other condition here in red, all the nodes adopt this trust assumption. This here is the classic formalization of this. We can say a subset of these participants of these nodes are a quorum system if any 2 quorums, the queues here, these are sets of nodes, they have an overlap such that for any set of faulty parties, if we remove the set of faulty parties from this overlap, there is still one correct node surviving in our overlap. This is the condition here, the consistency property. And the second property, like always in computing, we need safety and liveness. The second property is the liveness property. For my assumption here, for every quorum, for every node that could fail, for every set of nodes that could fail, we need to exist a 1 quorum that is live, that will not fail. So this is how we also call it a symmetric trust assumption also, because everybody would adopt this. And that's something that has been relaxed as well. We can relax this as well. And I want to motivate this as a basis for where we can go further. In my abstract, I realized when I prepared the talk that I was too ambitious about the 25 minutes because I wanted to show 3 extra results that we had from this. I'm going to talk only about one of them. Okay, so asymmetric trust is still the basis for what one could go on for. Asymmetric trust says, oh, what if I make my own trust assumption? What if I have a different trust assumption from you? Yeah, and so we relax the previous model, we extend it, and we let each node in the system define its own quorum system. So each node has now a quorum system just like before. Let's look at the example. Maybe that's easier. So P, we're talking about P. P down here has now a geographical representation, sort of. It has closed nodes like P and like Q and R, and nodes that are further away, the X, Y, Z. So the ones that are further away, you trust them less. You're going to say, oh, any 2 of those 3 might collude against me, but my neighbors here, they're not colluding against me. My neighbors are going to be honest, or maybe one of them is colluding with me, but certainly not both. Yeah? That's why we have a different trust assumption in here, in saying the potentially faulty sets, the fail-prone sets that P declares here, are those that are marked with the red shade. That Q could fail or R could fail, but 2 of the others could also fail. So this is now the assumption that that P could make, and this gives us an assumption of who could fail that looks like this for P, and we can get an asymmetric quorum system if now each node makes such an assumption in that sense. So not all the nodes trust in the same way. Nodes may trust differently. And now returning again to the question that I asked before, why did you want to do this? Why did you want to have this? Well, not everybody has the same taste, right? You cannot argue about taste. Yeah? In Latin, de gustibus non est disputandum. Yeah, you cannot argue about it. I like fish, you like curries, and so yeah. Certainly, also, if you've ever worked in a bigger organization or you've argued about security assumptions in real-life systems, no 2 security officers can agree on what is a good security assumption. Yeah, same holds for security research papers. Yeah, because it's an assumption, right? But what holds in practice, that requires extra research and work. Yeah, but the same phenomenon shows also up in blockchain protocols, namely the Ripple system and also the Stellar system that is related to it. They started both with the explicit declaration that we let every node declare who it trusts. Yeah? And every node then has a certain set that it could trust. How we formalize this is the work that we're actually going to talk about here. And so we've formulated based on earlier work by actually Matthias Fitz, who is also here, and together with Damgaard and Desmet, actually also Nielsen, the ideas of asymmetric quorum systems where each node now has its own fail-prone system. We start from this failure assumption of each node. We have an array of such failure assumptions, and together these arrays, these failure assumptions have to satisfy certain properties, and then this consistency, that's a generalization of the other consistency property, namely that one quorum for me, because I have different quorums from you now, yeah? One quorum for me and one quorum for you has to intersect in a set that contains at least one more process than those sets that can be faulty according to your idea and according to my and according to my idea. Yeah? And the availability property here is that I need a set of processes, a quorum that is good for me to exist according to my fault assumption. Now, with this type of formalization, we can actually formulate the typical protocols that you guys develop for n bigger than 3f with this other more general trust assumption, and also with this asymmetric trust assumption. Consensus, reliable broadcast, like Bracha broadcast, in case people know the jargon. This can be formulated like this with distributed cryptography, threshold cryptography. Going to be a bit difficult, yeah. But such quorum systems also, it's something that was not so clear in the past in those blockchain systems that run, like Ripple and Stellar, whether or not from a fault assumption that you make and from a fault assumption that I make, whether we have a protocol, whether we're going to have a party. In this properties here, we can analyze from a declaration of the fault assumptions. We can determine based on these properties here that go back again to the classic literature 25 years ago, whether or not this gives a consistent protocol, whether or not we have a quorum system actually. Yeah, I'm not going to talk about this now. Huh? The important thing here is that this, like the previous one, so that the previous the condition here for the symmetric trust, yeah, is that no three of the potentially faulty sets must cover the set of all participants. Yeah, this is the strict generalization of the n bigger than 3f. Yeah, any 3 times f. Yeah, and now no 3 sets must cover the set of all processes. Yeah, because there has to be one extra that is for us then to use to establish consistency. So returning to the picture from before, we can now realize that this can be extended to a asymmetric quorum system where from the P's position, it looks like this, and then we rotate the picture like that, and this is actually an asymmetric Byzantine quorum system like this. Anyway, what I wanted to mention, but will not have time to, is here. When you run such protocols, you have to think again about or when you formalize such protocols, about what it means to participate, because in traditional protocols, we only have correct nodes and faulty nodes. Faulty nodes, we don't care about them. We have correct nodes, we care about them, and all correct nodes are given the good properties. All correct nodes are going to succeed in the protocol. Here is a different third kind of node, namely the naive nodes, which are correct but have the wrong friends. Yeah? And this, for those, we have to make assumptions now in this type of protocol. So we want to, actually, we cannot get anything, we cannot guarantee much about the naive nodes. We only have to care about the so-called wise nodes, who are the correct nodes that also make the correct assumptions. I want to talk about now about one of the extra results that we can take from this model and extend. What if we have 2 systems, like 2 blockchains, for example, both running consensus, and both not having the type of majority quorums, but generalized quorums? How do we compose their trust assumptions such that we get a new system that respects the individual trust assumptions about that were in both of those networks, right? We typically hear of blockchains forking. We haven't really heard of many of them merging. Well, there's something going on with the merge, but I don't think they're going to merge quorum systems. But this is basically what it means. How do we compose, mathematically speaking, but with real-world applications, such quorum systems? So you have one network that consists of nodes P prime, and there are P double prime, a second network. And each of these networks has its generalized fault assumption, so fail-prone system declared. And now we want to merge them, and we want to make sure that their trust assumptions are respected. Here's an example. This is symmetric now, but generalized, right? So here's the fault system. The fault here are the fail-prone systems. There are two systems, A, B, C, D, E is one, the blue, and the green one is another system. But notice there are two of them in the overlap. If there is no overlap, that's actually easier, right? But still an interesting, somewhat interesting question. So in F prime, A could fail, or B and C could fail together, and so on. In F double prime, D could fail, or E could also fail alone. It could not, here also E could fail jointly with D. How do we join them? Yeah, we could just try to take the union of all these fail-prone sets, right? We could just say, okay, now we have the union of the participants. Now we also join the fault assumptions, yeah, but then we haven't gained anything. We have not gained any much because the new system hasn't gained any additional resilience. Yeah? We are not tolerating more than before. We just have more participants. Yeah? This would be the sets that are tolerated in this. And then if you think about what this would mean for the classical type of threshold systems, it would mean that we join two sets of 10 nodes, and we still can tolerate only 3 of them in the resulting join system. This is not going to be what we want, right? We want to achieve something better. Huh? Now, in the threshold model, since the world is so uniform, actually, if we are joining two systems of 10, you can do the math and find out then we can actually tolerate any coalition of any 6, yeah, any 6 nodes. This is not going to be maintained what we want to do here, because here we want to respect the local failure assumptions, yeah, that my neighbor who I didn't trust, I don't want to trust it much more. So this is not more power. So let's try another idea, namely the Cartesian composition, where we would just like pair every fail-prone set, every potentially faulty set in one in P prime, with each one in P double prime. So this is the Cartesian product there in the middle, right? So we pair all of them, and definitely gives us additional power, because for something that is tolerated in one system, we could also tolerate it in the second network, and their combination should be tolerated now in the joined network. That will not work though, as we recognized, because if you look into it, then we have paired here in the picture here, A with F and G in the top layer. In the middle one is a potentially faulty set B, C with H. This is also B, C with H could be faulty, and C, E together with D. C, E were in the blue one, and E is in the green one. E is one of the nodes in the overlap. This is actually the problem here with E. These nodes here, one of them shows up twice. That's why there are 9. But there are 8 nodes. These 3 potentially faulty sets, they cover the whole space of participants in the joint system. There is no protocol. Huh? This so-called Q3 property will not hold. That means this composition did not work. Huh? So we have to use a different rule. We want to use a different rule. And the key to seeing what happens here is that if a node shows up in a faulty set in both, yeah, then it must only be there with the same, in the same local constellation, right? So we include a joint set, from a faulty set from P prime or from F prime with one of the other, if and only if those nodes in the overlap are the same on both sides. So that's why we would not pair it, for example, here with the CE and the CE node. That's if we do this thing here, then we're getting a composition that actually works and that respects the properties of the Byzantine quorum system. Here it is shown, right? We include all those that where the C and C double prime contain the same common nodes, and this thing here are the sets that we're going to tolerate in this composed system, in this composed consensus system, and this satisfies that so-called B3 property, so we are going to have a protocol, and it's fine. This was only the symmetric trust, the generalized but symmetric trust, but we can also extend this to the asymmetric model, which is what actually interests us, yeah? Because there it may not be the case that two nodes have the same node, that two groups of nodes know exactly the same other participants. The details in the asymmetric case are quite a bit more complex, so I'll refer you to the paper for them. And I'm going to talk about one more thing before taking some questions, namely about permissionless and asymmetric quorum systems. Because we have talked now about asymmetric trust, but there was this innocent assumption that we had also before, namely there was a universe of nodes that was already known. And this may not be the case. This is particularly not the case in the Ripple and the Stellar formalizations. Well, formalizations in the sense that there is code that runs, so it's a formalization in some model. What if we don't know the set of participants ahead of time? In particular, we cannot evaluate then this Q3 or B3 properties. Yeah? Every node only knows its friends, and you know other friends. And this is this current work that is not yet available outside, but you can ask me for questions also with Giuliano Losa, who is here. The idea would be, the idea in this work is to unify the asymmetric model with the Federated Byzantine Agreement Systems in Stellar in the production system, but also with the formalization of personal Byzantine quorum systems that was at an event at a conference some time ago. Last but not least, yeah, well, you don't have to take pictures of the slides because actually you can find them on my homepage even, yeah. Yeah, because Joachim wanted them to download, so I thought the easiest thing is to just put them online. Trust not only by numbers, there are also other ways to define trust in our systems. Here are 3 papers where you can explore more about this. And the actual thing I want you to remember is this, because from there you can read and find all the references. Yeah, thank you. Great.